Let's recall that in Monte Carlo estimation, we are interested in approximating the theta, which is equal to the integral of g of x dx over some region A. The region A can be bounded, or it can be unbounded. Further, let's let x be a random variable such that f of x, its probability density, is greater than 0 for any x that is in the region A. In other words, A is either equal to the support of fx, or the region A is a subset of the support for x. In this case, the integral over A for g of x dx is equal to the integral over A of g of x divided by fx times fx dx. And that is equal to the expectation of the ratio between g of x and f of x, where x follows the distribution with density fx. Okay, so our theta is again a expectation of some function of random variables. So in order to estimate expectation of gx divided by fx, we can use the sample mean. Let's propose an estimator theta hat, which is equal to the sample mean of n rows of x from the distribution f. In other words, in order to approximate theta, we can draw x1 all the way up to xn from the distribution with PDF fx, and then we can calculate g of xi divided by f of xi for each of the i's, and then taking the sample mean gives us an estimate of our theta. You can see that, like the simple Monte Carlo estimator, theta hat obtained this way, which is a sample mean, is a unbiased and consistent estimator for the population mean, which is our theta. You can also see that the simple Monte Carlo estimator is actually a special case for this, where our x's follow the uniform distribution between a and b, and f of xi for any x between a and b is given by 1 divided by b minus a. So here are the explicit procedures for obtaining theta hat. The first step is to sample x1 all the way up to xn from the distribution f. Next, we want to compute g of xi divided by f of xi for each of the xi's I between the 1 and n. In the third step, we want to take the sample mean of what we obtained from step 2. And that will give us theta hat, which is equal to the sample mean of these g divided by f's. So one question you might ask is, in general, what makes a good f? We know that the uniform density can be one choice of f, but as we talked about, this might not be the most efficient f that we can choose. So recall that for this week, we are interested in obtaining a theta hat that is efficient. Efficiency implies low MSE. So how can we choose an f so that the MSE of our theta hat is as low as possible? Because theta hat is unbiased, choosing a theta hat with low MSE amounts to reducing the variance of theta hat. The variance of theta hat is given by the variance of 1 over n, the sum of all the gxi divided by fxi's. And that you can show that this is equal to 1 over n times the variance of g of x divided by f of x. So when is the variance of g of x divided by f of x small? Well, in your intro to statistics class, you learned one thing, which is the variance of a constant is equal to 0. So if there's no variation in g of x divided by f of x for any possible x values in the support of the random variable x, then we know that g of x divided by f of x will be, so in that case, the variance will be small. So the variance of this ratio will be small when g of x divided by f of x is approximately a constant over the support of x. In other words, this is when fx is approximately proportional to g of x across the entire support of x. So the fx function, which is the distribution we want to sample from, is called the importance function, or the importance sampling function. The idea behind importance sampling, which is obtaining the thetas using this method, is that certain values of the random variable have larger impact on theta compared to other values. So if these important values are emphasized by sampling more frequently, then the estimator variance can be reduced. Note that the variance of g of x divided by f of x is minimized when fx is proportional to the absolute value of g of x. This is what we mentioned in the last slide. But we have the absolute value signs over here because the density has to be non-negative. However, the g of x function that we are trying to integrate can take negative values. So when this is the case, so when fx is proportional to the absolute value of g of x, then because the probability density have to integrate to 1, we know that fx will equal to absolute value of g of x divided by the integral of g of x over the support of x. However, we cannot really obtain the fx using this method. We cannot directly use this fx, which is equal to this, because the denominator, this, is exactly what we are trying to estimate. So most of the times, we will have to choose the f using another way. And a good f will be one that has a similar or the same support as a, and at the same time, it is roughly proportional to the function g of x.